All right, so in 11.9, we're going to be talking about representations of functions as a power series. So we're going to start right in on an example, but the key for all of the stuff that we're doing in 11.9 is based on the geometric series. So our key idea is the following. A is going to be the sum of a geometric series. So if we start with a general geometric series, so our general geometric series is the sum as n goes from 1 to infinity of a times r to the n minus 1. And that's the normal way we write a geometric series, and we know that this converges to a over 1 minus r, provided the absolute value of r is less than 1. We will reindex the series and assume that a equals 1. So if we let a equals 1, we get the following statement. The sum as n goes from 1 to infinity. If a is 1, it's just r to the n minus 1, and then that would equal 1 over 1 minus r. But we want our series to start at n equals 0, not at n equals 1, so we're going to let k equal to n minus 1, and if we did that, then our series would look like this. So then k so if we plug in our n, 1 minus 1 is 0, infinity minus 1 is still infinity, and if we replace n minus 1 with k, we just get r to the k. And that's actually not going to change the sum of the series. We just wrote it a little bit differently. And if you write those out, they would generate the same series, which is 1 plus r squared plus r cubed, and so forth. And since that is a dummy index, we can rewrite it again as an n, which is the traditional way to write this as so. And if we look at our sheet of known series, we'll see that instead of using r, they use x, and we're going to have the sum as n goes from 0 to infinity of x to the n. So we really get the same idea, and we'll replace those r's with x's. So this is the sum of our geometric series. So this is a geometric series right here. And that's going to be the basis of what we are going to do. So starting with that idea, we want to express this function 1 over 1 plus x squared as a power series. So if our base series is f of x is equal to 1 over 1 minus x, but the series says that f of x is also the same thing as the sum as n equals 0 to infinity of x to the n, these two things are the same. We want to find this series, right? So we had g of x is 1 over x squared. So our question then becomes, how can we use function algebra to express g in terms of f? So if we look at that, well, what would I need to do to f of x to make it look like g of x? Well, f of x is 1 over 1 minus x squared, and this is 1 over 1 plus x squared. So we would have function composition. So g of x is f of x composed with negative x squared. So in symbols, g of x is equal to f evaluated at negative x squared. Because if I replace all of my x's in f with a negative x squared, that would give me 1 over 1 minus x squared, which would be 1 over 1 plus x squared, right? Which is exactly g. So we can use the fact that we know f of x is also this convergent geometric series. So the series representation is, we're going to take our f right here and replace it with negative x squared. So we have the sum as n goes from 0 to infinity of negative x squared to the n. And negative x squared is the same as negative 1 times x squared. So we could then rewrite this as negative 1 to the n times x squared to the n, which would finally yield negative 1 to the n x to the 2n. So that would be our series that represents that function. So 1 over 1 plus x squared as a power series would be this. And we want to find its radius of convergence. Well, what did we start with? Well, this was a geometric series, and a geometric series always has radius of convergence 1. So we could do the root test if we wanted, but since this is based on a geometric series, and that's our r, so our r is x squared, and we know that the absolute value of r has to be less than 1 for a geometric series to converge, and that comes from up here. So our geometric series converges if r is less than 1. But if our r is x squared, that's when x squared is less than 1, which would imply negative 1 is less than x is less than 1. So our radius of convergence would still be 1. And like I said, if you use the root test, you will also get the same thing. All right, let's take a look at our next example. So example 2. So we want to do the same thing here. Express 5 plus x as a power series and find its interval of convergence. So once again, our goal, just like what we had here, is we know that we have that f of x is equal to 1 over 1 minus x, which is the geometric series, the sum as n goes from 0 to infinity of x to the n. So we want to express this as something in terms of f. So we need to use some algebra to get it in the form of f. So the key thing we'll notice is f has a 1 and then minus our variable. And here we have a 5. So we're going to use algebra to factor a 5 out of the denominator. So if we factor a 5 out of the denominator, so 5, then that would leave a 1 plus x over 5. And then we could rewrite this as 1/5, as we could make that into a fraction. So we factored it out of the denominator, times 1 over 1 plus x over 5. But now we also need it to look like this, so we need it to have a minus sign. So we're going to rewrite positive x over 5 as a minus a negative x over 5, because a minus minus is the same as a plus. So finally, we end up with 1/5 times 1 over 1 minus a negative x over 5. So now we finally have it expressed in the way that we need. So to get this in terms of f of x, it is going to be 1/5 times f evaluated at negative x over 5. So this is composition with negative x over 5 and multiplication by 1/5. So if we put those two things into our series, we're going to have 1/5 times the sum as n goes from 0 to infinity of negative x to the 5th, or negative x over 5 raised to the n. So in this case, our r is negative x over 5, and if we wanted to, we could simplify this up a bit. So it's worth noting that this is our common ratio. And we know that a geometric series converges if and only if the common ratio is less than 1 in absolute value. So we would need to be less than 1, so that would be negative 1 is less than x over 5 is less than 1. And if we multiply everything by 5 to clear our fractions, we then get negative 5 is less than x is less than 5. So that would be our interval of convergence, would be from negative 5 to 5. All right, so our next one is going to be a U-try for you guys. Well, let's go ahead and express this as a power series and find the interval of convergence. All right, so the first thing we need to do for this is we factor out the 1/3, or the 3 from the denominator, giving us 1/3 times 1 over 1 plus x to the 4th over 3. And then we rewrite our positive as a minus minus, so 1 minus a negative x to the 4th over 3. So then we would recognize this as 1/3 times our f evaluated at negative x to the 4th over 3. And our common ratio r would be negative x to the 4th over 3. So our series representation would be 1/3 times the sum, as n goes from 0 to infinity, of negative x to the 4th over 3 raised to the n. And if we wanted to, we could split this up into a few different parts. So we would have negative 1 to the n, x to the 4th to the n, all over 3 to the n, which would be 1/3 times the sum, as n goes from 0 to infinity, of negative 1 to the n, x to the 4n, all over 3 to the n. And if you really, really wanted to, you could put the 1/3 back in and change this to an n plus 1. And that is common, although not required. So then we would have this as our series, and then we would need to have our absolute value of r less than 1. But since x to the 4th power is always positive, we know that that's going to be bigger than 0. So then we would multiply both sides by 3, and we get x to the 4th would have to be less than 3. And then we would take the 4th root, not the cube root, of each side. So then x would have to be less than the 4th root of 3. So then that would give us that we would have to have our interval would be negative 4th root of 3 is less than x is less than the 4th root of 3. And that would be our interval of convergence. So our series would converge inside that radius, and then outside it would not converge. All right. So let's take a look at our next example. So example 3 says, express x to the 3rd all over 3 plus x to the 4th as a power series. And if we notice, that is almost exactly the same thing that you just did in u try number 1. In fact, the only thing that's different is that it has an x to the 3rd. So this is similar to the u try. So specifically, this is u try 1 multiplied by x cubed. Because if you wrote it this way, it's x cubed times 1 over 3 plus x to the 4th. Well, we know this series. So then we'll replace it with what we know from the previous one, which was the sum as n goes from 0 to infinity of, and we had negative 1 to the n, x to the 4n, all over 3 to the n plus 1. And then now, if we distribute this in, we would end up with the series n equals 0 to infinity, negative 1 to the n, x to the 4n plus 3 all over 3 to the n plus 1. So we get a new series from an old series. So this is where this series list that we have here is going to come in handy. Oftentimes, we're going to need to build a new series, but if we know a series for something, we can use it to build a new series if it's just a product or something like what we just saw. So keep that in mind. We don't always have to build these things from scratch. So we have some of those series that we'll be able to use. All right. Our next example is going to use some theorems, namely the following. Our next theorem tells us when can we take the derivative of and when can we take the integral of a power series? And if we do, does it change anything about the power series? So our theorem says the following. If the power series, the sum as n goes from 0 to infinity of Cn times x minus a to the n has radius of convergence r greater than 0, then the function defined by that power series is differentiable and integrable on the interval of convergence, and the derivative is equal to the derivative of the power series, and the integral is equal to the integral of the power series term-wise. So this is kind of heavy, but what it really tells us is if we have a power series representation of a function, we can take its integral or its derivative and of the power series, and it will equal the integral or the derivative of the function on the radius of convergence. So this tells us that we may move the derivative and the integral operators through the summation sign. That is, for power series, the derivative of the sum is equal to the sum of the derivatives, and the integral of the sum is equal to the sum of the derivative of the integrals. And then we have a warning that says that the theorem states that the radius of convergence is the same, but the intervals may be different. Specifically, convergence may change at the end point of a series. So the reason this is really cool is when we have a series representation of something, a series is just a polynomial. And the polynomial rule for derivatives is really easy. We just bring the number down in front and subtract 1 from the exponent. So basically this says if we can write a function as a power series, we can integrate it or differentiate it term by term, and the integral or derivative still has the same radius of convergence as the original series. All right, well, let's see what some implications of that are. You may or may not remember this, but a while ago, we were looking at the alternating harmonic series, and I told you that I knew that the alternating harmonic series converged to the natural logarithm of 2. Well, we're going to find out why that's the case right now. So we want to find a power series for the natural logarithm of 1 plus x. And we don't have any rules that help us do that. The only thing we know is that we have f of x is equal to 1 over 1 minus x, which is equal to the sum as n goes from 0 to infinity of x to the n. Well, none of these look like that, but if we call this guy g of x, we do know, well, g prime of x would then be the derivative of the natural logarithm is 1 over the inside. So g prime is equal to 1 over 1 plus x. Well, that is equal to f evaluated at negative x, because we replaced our x with negative x, so this would be the summation as n goes from 0 to infinity of negative x to the n, which would be the sum as n goes from 0 to infinity of negative 1 to the n, x to the n. Okay, well, we now know that g prime of x is equal to that series, right? Well, we want g. Well, g of x would then be the integral of g prime of x dx, which would be the integral of that series. So the sum as n goes from 0 to infinity of negative 1 to the n, x to the n dx. Our theorem says that we can interchange the integral and the summation sign. So by our theorem, we can interchange the sum and the integral. So then that would give us that g of x is equal to the sum as n goes from 0 to infinity of the integral of negative 1 to the n, x to the n dx. Well, we're now integrating this with respect to x, so the negative 1 is a constant because it's indexed on n, not x, so that can actually come out of the integral as well. So then that's negative 1 to the n, the integral of x to the n dx. Well, what's the antiderivative of x to the n? Well, we add 1 to the exponent and divide by it, plus we get a constant of integration. So we get c plus the sum as n goes from 0 to infinity of negative 1 to the n, and then the antiderivative of x to the n is x to the n plus 1 divided by n plus 1. So we get c plus the sum as n goes from 0 to infinity of negative 1 to the n all over n plus 1 times x to the n plus 1. So that would be g of x, which we know is equal to the natural logarithm of x plus 1 is equal to c plus the sum of the series n equals 0 to infinity of negative 1 to the n, x to the n plus 1 all over n plus 1. Well, we would like to know that constant of integration. So if we let x equal to 0, that gives us the natural logarithm of 0 plus 1 is equal to c plus the sum as n goes from 0 to infinity of negative 1 to the n, 0 to the n plus 1 all over n plus 1. But what is this series going to add up to? Well, every single one of them has a 0 in it, so it's going to be multiplied by 0. So now that adds up to 0. And the natural logarithm of 1 is 0, so 0 is equal to c. So that means our constant of integration is c. So the natural logarithm of x plus 1 is equal to the sum as n goes from 0 to infinity of negative 1 to the n, x to the n plus 1 all over n plus 1. So it's worth noting, if we let x equal 1, that gives us the natural logarithm of 1 plus 1 is equal to the sum as n equals 0 to infinity of negative 1 to the n, 1 to the n plus 1 all over n plus 1. So simplifying, that's the natural logarithm of 2 is equal to negative 1 to the n. 1 to any power is 1 all over n plus 1. Well, this is 1 minus a half plus a third minus a fourth plus dot dot dot. That's the alternating harmonic series. So that is why we know that the sum of the alternating harmonic series is equal to the natural logarithm of 2. Because we were able to express the natural logarithm of x plus 1 as a power series. And when we plugged in the specific value x equals 1, it generated the harmonic series, but we know that we could have plugged that into our original function, the natural logarithm of x plus 1, which gave us ln 2. So the ln of 2 has to equal that series, which was the alternating harmonic. So we were able to successfully sum that series and find its value. All right, so it's now your turn again. So we want to do something similar and find a power series for the inverse tangent of x. All right, so to find a power series representation for the inverse tangent of x, we still need to use a geometric series. But this isn't exactly in the right form, which is 1 over 1 minus x. But if we take the derivative, we have that f prime of x would be 1 over 1 plus x squared, which, if we wrote this as a power series, we would have the sum as n goes from 0 to infinity. Our r would be negative x squared raised to the n, because this is minus a minus x squared. So then we split those up a little bit, and we get negative 1 to the n and x to the 2n. So our power series for f prime, which is 1 over 1 plus x squared, is the sum, as n goes from 0 to infinity, of negative 1 to the n, x to the 2n. But we don't want f prime, we want f. So to undo that, we would take the integral. So the integral, so f of x is equal to the integral of f prime of x dx, which would be the integral of the sum as n goes from 0 to infinity of negative 1 to the n, x to the 2n dx. But then we interchange our integral and our sum, and rewrite negative 1 to the n can come out, negative 1 to the n, the integral of x to the 2n dx. So then the antiderivative of x to the 2n is we add 1 to the exponent and we divide by it. So that's going to be x to the 2n plus 1, all divided by 2n plus 1, plus our arbitrary constant c. Once again, if we try f of 0 would be the inverse tangent of 0, which would have to equal this series evaluated at 0. So we replace all of our x's with 0. So 0 to the 2n plus 1 all over 2n plus 1 plus c. Well, this series would have to be 0. We know that the inverse tangent of 0 is 0, so this gives us 0 equals 0 plus c, so c has to be 0. So finally, putting all of that together, we get that our series for the inverse tangent of x is just the sum as n goes from 0 to infinity of negative 1 to the n, x to the 2n plus 1 all over 2n plus 1. So that was our geometric series, and then we integrated it term by term to get this. And if you check on our list back here, we actually have both of those last two examples that we had. Here we have our inverse tangent, negative 1 to the n, x to the 2n plus 1 over 2n plus 1, and that gives us our series that we have here for arctangent. So once again, we can find some pretty interesting sums. So for example, if we let x equal 1, the inverse tangent of 1 is pi over 4. So then pi over 4 would be equal to this series evaluated at x equals to 1. So negative 1 to the n times 1 to the 2n plus 1 all over 2n plus 1. But 1 raised to any power is just going to be 1. So the series n equals 0 to infinity of negative 1 to the n over 2n plus 1 equals pi over 4. That is, pi over 4 is equal to 1 minus a third plus a fifth minus a seventh plus a ninth minus dot 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 on forever. If you added up that entire infinite series, you would get pi over 4. Moreover, if you multiplied both sides of that equation by 4, you would get an infinite series that would add up to the number pi. It converges very, 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 very slowly, by the way. But eventually it would get you to pi over 4. And we'll note, since this is an alternating series test, the error is always less than the next term. So you would have to have quite a few terms to get any accuracy at all. All right, so speaking of accuracy, let's take a look at our next example. So example 5. Evaluate this integral as a power series and then approximate the definite integral from 0 to 0.5 of 1 over 1 plus x to the 7th correct to 6 decimal places. So one of the things that we found earlier this semester is that there existed certain functions that didn't have elementary antiderivatives. That means that regardless of what technique of integration we used, by parts, U substitution, trig substitution, whatever, it was impossible to find an antiderivative. Well, if we can represent a function as a power series, the other implication of that theorem that we just had is that we can use the power series to find a series representation of that integral and then evaluate it to whatever accuracy we need. So we want to evaluate the integral of 1 over 1 plus x to the 7th dx. Well, 1 over 1 plus x to the 7th would be 1 over 1 minus a minus x to the 7th. So in terms of a power series, that would give us the sum as n goes from 0 to infinity of negative x to the 7th to the n. So 1 over 1 plus x to the 7th would be equal to the sum as n goes from 0 to infinity of negative 1 to the n, x to the 7n. So if we integrate both sides of this, that would be the same as, and we can interchange our summation and our integral, negative 1 to the n, the integral of x to the 7n dx. So then as always, we take our antiderivative of a polynomial using the polynomial rule, which is we add 1 to the exponent and divide by it. So we get x to the 7n plus 1 all over 7n plus 1. Plus an arbitrary constant c, but since in part b we are going to approximate the definite integral, we don't need the plus c, right, to use part 2 of the fundamental theorem of calculus. So this is our antiderivative of 1 over 1 plus x to the 7th. So it's not an elementary antiderivative as it is expressed as an infinite series, but that is an antiderivative for that. So now, to do our definite integral, we would have the integral from 0 to 0.5 of 1 over 1 plus x to the 7th. Well, if this is the antiderivative, it's this evaluated at b minus this evaluated at a. So I'll call this my capital f of x. So this is f of 0.5 minus f of 0. So then that would give us the sum as n goes from 0 to infinity of negative 1 to the n this way, 1/2 to the 7n plus 1 all over 2n plus 1 minus the sum as n goes from 0 to infinity of negative 1 to the n over, sorry, that's 7n, I wrote it as a 2, 7n plus 1 0 to the 7n plus 1, but 0 times anything is going to make that sum equal to 0. So the value of this antiderivative then is the sum of this series. Is equal to the sum as n goes from 0 to infinity of negative 1 to the n 7n plus 1 times 2 raised to the 7n plus 1. So the sum of that series is the exact value of the integral. But we only need to approximate it accurate to 7 decimal places, or to 6 decimal places. So to 10 to the negative 7th. So we know that the error by the alternating series test the error is always less than the next term of the series. Let's just do it this way. Less than the absolute value of an plus 1. So the absolute value of an plus 1 is the negative 1 to the n is going to be positive 1. So it's going to be 1 over 7 times n plus 1 times 2 to the 7n plus 1. And if we grab our calculator, and we put in our so 7x plus 1 times 2 to the 7x plus 1. So that's the absolute value of our next term. And if we try a few of these, so we go alpha trace, so that gives us, that's not going to be enough. We try 2, gives us this. In fact, we'll probably just do a table. So we'll see at n equals 2, we get 10 to the 6th. So we need it less than 10 to the 7th. So looking at our table, so that's going to be here. So our n is going to be, our n plus 1 is going to be 3. So our error will always be less than the next term. So n plus 1 equals 3, so n equals 2. So that means if we were to take our sum of that series, so we've got it in here, and add up the first couple of terms, so we go sum as n goes from 0 to 2 of, now we got to go back to our original series, so -1 to the n all over 7n plus 1 times 2 raised to the 7n plus 1. And we get this value. So 0.499517, blah, 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 blah. And that would be the sum of our series with the desired accuracy. So just to see, if we go second entry, and we go back to the very beginning and we change the sum from 2 to 3, come back. We'll notice that 1, 2, 3, 4, 5, 6, the first 6 digits, in fact, the first 7 are still exactly the same. So the minimum number of things we had to add up was the first, from n equals 0 to 2. If you went n equals 0 to 3, you're only adding up 4 things. It doesn't really change the value of the integral. And that's what the alternating series test said, that we could actually approximate this with only 3 terms. So we were able to have 6 decimal places of accuracy by just adding the first 3 members of the sequence up, or of the series up, as an approximation. So that's really the biggest utility with series.